Matheus is going to try to convince us to buy the programmable
No,
routers.
Never said that.
So he's going to present a paper called "The Case for Network Accelerated Query Processing." So Matheus, feel free to start.
Let me, by the way, say about this that Philippe he talked to me at Cider, and I'm not sure what you're going to say about this paper, but he actually invited people who would like to work with him, maybe to go to Switzerland or something, interns or whatever.
That's how Matheus
if
got
you're
rich.
if you're really interested after this talk, maybe, and you really want to do that, whatever.
I got the same feeling from Alberto because I talked with him. He kind of said the same thing. Yeah. Okay. So I think Alberto was a guest PhD student here some time ago. Anyways, so when the first, all right, it was right. So when the first time I looked at this paper, I said, "Well, look, nice, cool paper. Different way to play with the data and new hardware. It's something I like. Don't know why, but every time, every time that there is a new way to process something, there's always the old way, and I did not understand. So let's go through it and see if maybe you can help me, maybe if it's correct or not." So we have our little cluster here. You have the switches. You have one switch that connects every node in the cluster. And then, now that you have this kind of programmable switch, what was the role of the old kind, or the old type of switch? So the answer is kind of trivial. It was just message passing, did nothing else. So did the network care about the content of packages? No, it was neutral, as it should be. But this wasn't a problem, because we have distributed parallel databases. This wasn't invented now, and it was all working fine and dandy. So, and if you read recent papers about the topic, you also see a lot of mentioning about this fancy thing called InfiniBand, which apparently makes your memory bandwidth comparable to your network bandwidth compared to memory bandwidth. So, everything's fine, no problem solved. So this raises the questions of where you actually going to put these programmable switches, why using them, and what kind of benefits it brings to the table. So to understand this, I'm going to try to do something a little bit different. And we're going to talk about work, going to the gym, and going to the supermarket. Because this is this is the kind of thing I do on my day. This is my day. Let's say you have your beautiful home, the nice place that you work, the gym that you go, there you get your weights and you train. That's what you do there. And the supermarket, where you get food and you pay. And in this loony town, we have one central station, and to go from one place to the other, you always take the train, and there's one station and no roads. So let's say you start your regular day, your rainy and windy and beautiful day, and then you leave home, and now you want to go to work. It takes 5 minutes, you work there, fine. Then you return home, and now you want to go to the gym. After work, like any sane person does, then okay, you go there, you get your weights, you train, you return to the central station, because now you need to get food. So you go to the supermarket, get food, pay, return to the central station, and get home. And on this nice day, you spend 60 minutes doing absolutely nothing, just commuting. So yeah, how do you solve this? Can you improve this? There's two ways you can do this. The first one, you can protest for better trains. Well, good luck. Getting better trains is usually expensive, and worst case, they might not be available. Or you can bring the action to your path. It's basically you go to the central station, you work at the central station, and you buy at the central station. So now we have our shiny central station. New central station. And we start at our beautiful home, we go to the central station, we go to work, there's nothing you can do about that. And you return to the central station, but now someone got your weights there. So the only thing you need to do is train. Now, someone also got your food there. So the only thing you need to do is pay at the central station. You don't need to pay the price of going there. And then you return home. And now your transit time, which is commute time, is 35 minutes. Now, what's the difference here? We did not increase the speed of the trains, we did not increase the number of the trains, we just changed it where we do the action. And this resulted in a decrease in transit time. And this is exactly what the programmable switch can do for you. It will decrease your latency. This was the example they had on paper, TPCH query 20, and this is the best accorded plan based on this paper here, but this is way too big to analyze, so we're gonna look only at a small part of it. And let's see how it would work on a regular database with 6 nodes, a switch in the middle, and the relations distributed like this. So the first thing you do is you get the parts relation, you group by, and you broadcast. You broadcast because it's a small relation. So every node that should receive parts, receive it. Now we're gonna look at node 1. Node 1 does a loop, a hash join, and a group by. It gets the group, and now it's time to redistribute and to the nodes that are relevant to the query. In this case, node 2 and 4. This was randomly selected. It could be number 5 also. It's just the example. Now, how would this would work if we had a switch, a smart switch? You have this deparse operation, which is basically get tuples and transform into network packages. And so now you start here, you do the group by as usual, you deparse and send to the switch. Now the switch has the relation inside of it, it builds the hash table, and now node 1 will get the line item, send to the switch will do the hash join, the group by, and send to the relevant nodes, all while the data is in transit, as you can see in this beautiful animation. And yes, that's it. Also, the other nodes will do the same, but I'm just showing node 1. So what we gain with this? Well, you decrease the transit time. Since the data is being processed while in transit, sending it through the network might actually be beneficial. A side effect is that the nodes are free to do other tasks because they're not processing, and they report a 2 times speed up compared to not using the switch on the paper. Now, how this switch works? Disclaimer that I don't know fully how the switch works because this is much more networking. So if you want to understand it, just watch this video from Nick, and he will explain why the switch works like this, what's the history, and you can see it there. So for now, we're going to just look at the very basic of it, the center of innovation, which is the MAUL, match action unit. This match action unit is a table. Here you're seeing an example from networking. So if you receive this MAC address drop, this MAC address forward to port 4. So the MAUL has the match engine and the action engine. The match engine simply gets fields from the packets and matches to one row. And then when there's a match, it does some kind of action that you also define. On older switches, as far as I could understand, this MAUL was written in stone. You couldn't change the size, you probably couldn't change the actions. You could more or less change the contents here. Yes, so how the switch works, this is the switch, you receive packages, they go through this thing, the deparser, which will get the network package and transform to some internal structure. Then you have the deparser, which does the opposite. You have the traffic manager, which is just sending packages around. And you have the MAULs, which is the ingress side and the egress side. They are the same thing, but some operations are only available on the ingress or on the egress. And when you put a bunch of MAULs together, you have this thing called data plane. And also every switch has this thing called control plane, which is a regular CPU that the network protocols use for something else. In the database, you can use for overflowing tuples that don't fit inside the switch. And the paper mentioned that the bandwidth between data plane and control plane is not that great, so it can be used, but it should be avoided. And they also mentioned the architecture of 64 port switch. So you have 64 ports, you have 4 groups, each with 16 ports. And inside the group, they share the MAULs and the parser, but between the groups, there is no sharing. And you have the traffic manager in the middle. If anyone has any questions, ask, because I might be going too fast or You guys might not understand it. So the system architecture, they propose this net Excel. It has a master node that communicates with the client, receives query and returns results, the default thing. Then you have the MPP nodes, which holds the data and execute queries. And you have obviously the programmable switches. Now let's look at this yellow thing is here. You have this network scheduler, which takes care of distributing the query plans to the nodes, to the control plane in case of overflow, and setting the switch with the correct actions. And obviously it receives results from the nodes and from the switch. This deparser is just the thing that transforms tuples into packages and packages into tuples. And these small operators is just a repository with the operations that can be instantiated in the query. Implementation is a hash table with a collision chain, but the collision chain is a linked list with defined size. Each mall is like a level on that chain. And in the end, you have a Boolean vector to keep track of overflows. It might seem strange, but I'll show an example and you understand how it works. So here we have the example. We have the algorithm here. Don't pay too much attention to it because we're going to go through it. We have the malls and we have a package on the top. So the first thing we look is this package an outer, which means, is this package to build the hash table? Yes, it is, and since it just entered, it hasn't been found. Now we check the first position, the position 0 from the hash. It's empty, yes. So we put ourselves there, and we drop the package because we don't do anything else with it. Now we receive another one, the pinky package. It's an outer, hasn't been found. Now we check the position 0, empty. No, so this is a collision. What we do is we check if the join key is the same. It's not, because one is join key, the other is join key 2. So we haven't been found yet, so we proceed to the join chain 2. And well, since there it's empty, we insert ourselves and we drop the package. We do the same thing with this black package, which ends up in this env, the env join chain. And now we receive the white package. Again, hash position 0 and a different join key. And as you may imagine, this one will result in an overflow, because it will go through each mall here until n, checking position 0 and seeing that they're all used and not empty. They're not empty and now used. So it arrives at the join chain flag, and it verifies this is an outer package, and this hasn't been found yet. So this results in an overflow. And this is redirected to the control plane, and yes. So now you have an inner package, which means it's probing time. So again, hash position 0, join key is the same as the first one. We go to the first mall, we check if it's the same as in this case, yes, it is. So yeah, fine. It proceeds, normal. Now we receive another package, again, a white one. It will go through each mall, checking if it's the same as you. Since it isn't, it will arrive on the join chain. And then, well, there is a true here, so it means on this position there was an overflow. So you need to go to the control plane and check if check if it's there. And now they have the group by, which is the second operation that they implemented. So in their example, the group has 2 attributes. That's why this mall here has 2 columns. The group has this presence, just to check if the position in the chain is occupied. And you have on the chain you keep track of the attributes, and on the aggregation is where you actually do the aggregation. And this is how you do a group by with one stage. It means it cannot handle collisions. If you want to handle collisions, you just add again this little group of malls. Again, it might make more sense here. You have again your algorithm, our group by, and packages, and here we can handle one collision. We start in the presence thing. Well, since there's nothing there, we insert ourselves, we put true there. Now we go to the second mall and we put our group by values there. And since we were inserted, we do the aggregation. Now we're gonna do the same for the pinky package. We check the first one here. Oh, there is something there. So we're gonna check what is inside of it. Well, pink's different than blue, so we don't insert ourselves there. So since we weren't inserted, we don't do anything here. We proceed to the fourth mode. And since this one is empty, we insert ourselves there and we do the aggregation. Now we receive the black one. And the black one will result in overflow because it will go through each of them on the position 0 and see that the colors, the values are different. So it actually ends in overflow. The experiments that they ran. So this was their setup. They had a master node that communicated with the client to receive queries. They had TPCH scale 100 data, uniformly distributed over 3 nodes. Each of these nodes had 126 gigabytes of memory and 100 gigabytes per second network card. And all of them were Greenplum parallel database segment nodes. And the first experiment that they ran was a comparison between running the hash join and the group by on the CPU and on the switch. So to do this, what they did was they removed, this was from query 20, so they wanted to just compare the hash join and they wanted to just compare the hash join and the group by on the switch and on the CPU. So they removed the projections and the selections that they had on the part and line item by using materialized views. And yep, and the result that they got was that it was 2 times faster to do it on the switch. There's not much explanation on what, or at least on why, or at least I did not understand it because it's a small paragraph saying, yes, 2 times faster. And then there's a little bit of explanation. And then the next experiment that they wanted to do was to quantify the overflow. Because if you give more moles to the operation, it can handle more tuples. So the first experiment, this one, had two stages for the hash join and 2 stages for the group. So they wanted to see if they could vary that and see what happens. On the horizontal axis, you have the group by stages, and on the vertical axis, you have the join stages. And on the middle, you have the percentage of overflow tuples. And the thing that you can see is if you increase the group by stages, there's absolutely no difference. But if you increase the join stages, then actually you decrease the overflow. And this makes sense because if you give more moles to the join, then it can handle more tuples, hence it will decrease the overflow. But if you give more stages to the group by, yes, it can handle more tuples, but all the tuples have already overflowed before it reaching there. So it doesn't matter. And the final experiment that they ran was to check the network speed influence. Here you can see, besides that, you can also see how much the accelerated plan influences the total query time a little bit. So on the vertical axis, we have the query response time in milliseconds. On the horizontal axis, the network speed. That original one is the plan that Greenplum chose. The best plan is the best corded plan based on this paper here. Then you have the accelerated version, which is the one using the network switch with no overflow tuples. And the mean is some kind of minimum threshold they calculated, but I could not understand fully how they did it. And the first thing that you can notice is that the original and the best plan don't change that much as you increase the network speed. And this makes sense because they optimize for as little data movement as possible. So if you move little data, then increasing the network speed doesn't change, will not do anything for you. But on the accelerated version, you can see a linear decrease in response time from 10 to 25 gigabytes per second. And after that, it's kind of stales because the deparser operator tops at 29 gigabytes per second, and then it becomes the bottleneck. So the conclusions that they had, it was that this was the first network accelerated. They presented the first network accelerated database management system. They opened new research areas, and they basically demonstrated that this can actually improve your query performance, although it needs more research. Thanks.